Hi friends, again MCL 142. Okay, so this lecture is going to focus on transient heat conduction. In the previous two classes, we actually looked at the derivation of the heat conduction equation and its steady state solutions. We had looked at the planar system, and we had looked at the cylindrical system and spherical system, and we had looked at extended surfaces and fins. So in today's class, we'll be focusing more on the time-dependent solution of the conduction equation. So where is it applicable? Take an example of heat treatment of a metal. So the metallic piece is actually put in a furnace and heated to a high temperature, and then from there it is taken and quenched into a bath of oil. So this is commonly done to make the surface of the material very hard. So the cooling rate of the surface, if it is very high, then the surface becomes hard. So for example, tools like knives or cutting tools of various kinds, the surface has to be as hard as it can be. So quenching is a process that is used. This is a heat treatment process. So for this, what do? They heat the material and then quench it into oil. So now one needs to see what is the rate at which the cooling happens. So this is a transient conduction problem. So any other problem where the time dependence of the heat transfer is important, we'll be looking at the solutions of the transient conduction equation. So with this background, let us start looking at the time dependent conduction equation and try to understand the physics of it before we go into the mathematics of it. I'll spend a few minutes trying to explain to you what the phenomenon is and what our method of analyzing it is going to be like. And after that, then we can start with the equation and its solution methods. So now let's switch to the screen of the whiteboard. So suppose there is an object which is initially at a temperature Ti at time t equal to 0 uniformly throughout the body. Now this at time greater than or equal to 0 is suddenly immersed into a medium whose temperature is T infinity. For the present case, let us take a case of, let us say, quenching of a metal from a temperature. So Ti is greater than T infinity. So it's a cooling problem. Okay. The analysis will be exactly the same even for the heating problem, where the object is cold and it is dumped into hot oil. For example, frying of a puri, for example, where you are going to put the atta that is shaped into the puri into the oil. It's again a quenching problem, but this is of the opposite kind, where the object that is put in is cold and the object that is the medium is hot. Both ways the solution will be the same. Let us analyze using Ti greater than T infinity as the case. Now what will happen? At time t is equal to 0, suddenly this surface becomes conscious, or rather becomes aware that there is a change in temperature that has happened. So if I look at close-up of the wall, so somewhere like this is T infinity, and far away it is Ti. At the surface, very close to the surface, let us say a very thin layer whose thickness we can call as, let's say, delta, would probably feel the effect of the boundary condition, and the rest of the material stays at the initial temperature Ti. So if I plot the temperature, okay, and let us take the coordinate in this direction normal to the surface at any location as x, then at time t is equal to 0, the plot is exactly this. So initially the surface is at let's say this surface is not exactly at this temperature, but let us say at some temperature T0. And for simplicity's sake, at the moment we'll take the T infinity and T0 to be the same. That is, we are considering that there is no resistance offered by convection on the outside. So the surface is at, let's say, T infinity or T0. We'll use these two interchangeably in this particular case. Okay. So suppose this temperature is T0, which is the surface temperature. Okay. So initial profile will exactly be this. Let's say this temperature is Ti. Okay. At some time later, you will find the process. You will find the profile, which goes something like this. So up to here, the body has felt the presence of the boundary, and inside the temperature still remains Ti. When time increases, this would go a little deeper like that. So up to this depth, you have seen the presence, you have felt the presence of the outside, and so on. So if I go at different times, as time increases, the profiles will go deeper and deeper. So this thickness, which I call delta, so this I call it as delta 1 at time T1, this I call it as delta 2 at time T2, this I call as delta 3 at time T3. As time increases, the delta goes on increasing, right? So this is what we call as, if I call this the skin layer, then the skin layer keeps on growing with time as you progress in time. And a time will come when this skin layer will eventually grow and engulf the entire body. So you get the whole body starting to move away from temperatures Ti. There will be no point in the body which remains at Ti, and the whole body now goes towards T infinity. Okay. So we have a time at which this last point at which temperatures Ti disappears. Let's say that time is T1. Okay. So at time T1, the last point in the domain goes off Ti. So there is no more point which is at the initial temperature inside the body anymore. So the time scale for that to happen is, let us say, T1. Okay. So now let's understand what is the phenomenon here. So now, when the time is much less than T1, that is the characteristic time scale for the entire body to be covered by the skin layer. If the time is much less, then it's only a small region close to the boundary which is being affected by the presence of the medium that's around it, and the rest of the body is at temperature Ti. And if I take this as the x coordinate, then as x tends to infinity, temperature becomes Ti, and in the finite values of x inside this domain, where the temperature variation is happening and therefore you actually need the solution of the equation, that region is much smaller as compared to this. So delta is much less than, let's say, R0, which is a typical characteristic dimension of the body. So in the figure here, suppose R0 is some cross-sectional dimension of the body, let us say this, right? So it can be, for example, for a sphere, the diameter of the sphere or the radius of the sphere. For a cylinder, depending on whether it is shorter or longer, it can be the radius or it can be half the length, and so on. So it can be various dimensions like that, and quite frequently this R0 while analyzing is also defined in the form of volume divided by surface area for any arbitrary body. This is also a possible way of accounting for a characteristic dimension of the object. So this is something comparable to the size of the object, and this is comparable to the size of the skin layer. So when the skin layer is very small as compared to the rest of the medium, you can consider the medium as semi-infinite. Okay, and because the time is much less than t1, you can consider it as an early phase. Okay, so in the early phase of transient heat conduction, we can use the semi-infinite approximation, which basically means that you have a surface here, and the surface starts from x is equal to 0 and goes to x tending to infinity. That is the extent of the domain, and the temperature profile will be plotted as a function of x. So if I plot t versus x, you would get the various temperature profiles at different times. So this is the thing that I was talking about. So this is something which is a semi-infinite body solution that is obtained for a domain which is x is equal to 0 to infinity. Right? So that is your thing. So your body is in de facto infinite as compared to the region which you are actually interested in. That's why it's called a semi-infinite object problem. In the other extreme, when the time is much greater than t1, then what happens? Much greater than t1, then what happens? So it is long since the entire body was affected by the presence of the boundary. So there is no more point inside the body which is at the initial temperature. So much so that you can actually consider the temperature inside the body to be more reasonably equal to each other at various points, and very different from the body, which is the temperature which is outside. So suppose I say that suppose this is my body whose center temperature is, let's say, Tc, and the surface temperature is T0, and the ambient temperature is T infinity. Then we can consider the difference between Tc and T0 as much smaller than T0 to T infinity. This is the case that would happen, in which case we can actually say that the body itself, the Tc and T0 are not so different as compared to the difference between T0 and T infinity, so much so that you can consider the body to be at one uniform temperature, let's say T of T. So this is what we call as lumping the body. So it's called a single temperature for the whole body is called lumping the body. So this method is called the lumped capacitance method, and that is applicable to what is called the late phase. Okay. So you see two extreme conditions here. One is for early phase, where t is much less than t1, and you use semi-infinite solid model. And when late phase, when t is much greater than t1, you use the lumped capacitance method. Okay, so that is the extreme. So when t is of the order of t1, which is neither in this case nor in the other case, you can neither use the late phase approximation nor use the early phase approximation. Then you have to solve the full equation of conduction. So this is the three regions that normally we would look at: the early phase, late phase, and the intermediate range, where the temperature is of the order of, the time is of the order of the characteristic time for the body. Now let us go back and try to estimate what this time t1 would be by doing an order of magnitude analysis on the governing equation for the particular problem that we are looking at. Okay, so Let us consider the one-dimensional transient equation. We had derived it in the previous class. So it is 1 over alpha del t by del t is equal to del squared t by del x squared. So what is the assumption involved here? The body is one-dimensional and the properties are constant. So the k that has come out from the right hand side and the rho c that came out from the left hand side combined together to give this 1 by alpha, which is alpha is the thermal diffusivity of the medium. Okay. So alpha is k by rho cv. This is something that we had looked at last class. This is called the thermal diffusivity. Okay. So now if I take from this equation and do an order of magnitude analysis. What is an order of magnitude analysis? We are not trying to solve this equation, but trying to look at what each term would be of the order of. How big is each term? And using that, getting an idea. It's not going to be an exact solution, but it will say what will it vary with, what is something proportional to, and so on. So it gives you a physical understanding of the problem, but not a quantitative but a qualitative understanding of the problem. Okay, based on some quantitative estimates or feelings that you would have from the understanding of the physics. So let us try to do that. So for example, let us take this term del squared t by del x squared. Okay, this is going to be del by del x of del t by del x. So I can say del t by del x, and we are looking at it in the let's say region of the skin layer. Okay, so it will be del t by del x at x is equal to delta minus del t by del x at x is equal to 0 divided by delta minus 0. Right. So this is your approximate expansion. So this should not be equal to. So you can say this is of the order of. Okay. So you'll use this symbol here, of the order of. So del squared t by del x squared, which is the right hand side of this equation, is of the order of del t by del x at delta minus del t by del x at 0 by delta minus 0. Now let us look at the orders of magnitude of this del t by del x at delta and del t by del x at 0. So we'll go back to the previous page where we had plotted some figures. So let us look at this figure. So or this figure. So at x is equal to delta, the temperature gradients actually seem to vanish, and the temperature becomes equal to Ti after that. So the del T by del x at delta is going to be of the order of 0, right? Because the temperature gradients disappear after delta, and therefore del T by del x at delta is 0. And del T by del x at T naught, if you want to get the order of magnitude, let us consider a straight line temperature distribution here. So the slope of the slope of this curve at this would be of the order of, not equal to it, but maybe a bit more than that because of the kind of the slope, but of the order of the slope of this straight line, which will be temperature at this location, temperature at this location minus the temperature at this location divided by this distance, which is delta. So it will be Ti minus T naught divided by delta, because x is increasing in this direction. So Ti minus T naught divided by delta minus 0. So that will be your del T by del x at this location 0. So if I use both of these in my final estimate of order of magnitude, what will I get? I will get this is of the order of 0, del T by del x at delta is of the order of 0, minus this will be of the order of Ti minus T naught divided by delta, that is of the order, divided by delta, which will be of the order of. So the minus will get absorbed here, T naught minus Ti divided by delta squared. Okay. So the right hand side of this equation is now of the order of T naught minus Ti divided by delta squared. Okay. Now let's go to the left hand side and see what the order of magnitude of the left hand side is. So the left hand side is nothing but 1 by alpha del T by del T, and for this region, if you look at the del T by del T, the temperature was initially Ti, and now the temperature is going to reach something which is comparable to T naught, So if I say the at time t, the temperature is T naught, and at the initial time the temperature was Ti, then the del T by del T is of the order of, again it's not equal because the temperature is not equally T naught everywhere, but it is T naught at one end and Ti at the other end. But if I say it's T naught at time t and Ti at the initial time, so this del T by del T will then be equal to T naught minus Ti divided by the time. Okay, so we'll get 1 by alpha del T by del T, which is the left hand side, is of the order of T naught minus Ti divided by alpha t. Okay, so this T naught is the temperature or order of the temperature at time t. Ti is the order of the temperature at time 0 divided by t minus 0 multiplied with this alpha. So now this is the left hand side, T naught minus Ti by alpha t, and this is of the order of, from the previous analysis that we did, T naught minus Ti divided by delta square. So if I put that here, T naught minus Ti divided by delta square. Now since the numerators are the same, you can say alpha t is of the order of delta square. Okay, so basically delta then comes out to be of the order of square root of alpha t, and this is a very interesting result because we have not done anything mathematically great, but we are able to get what thickness goes with as a function of time. Right? So it clearly shows the thickness would be proportional to the square root of time. There can be other numbers that get added here, and it will also be a function of square root of alpha. Right? So that's a very interesting result that we have got. So the thickness of the boundary, the skin layer at any given time t, delta of t is going to be varying with square root of alpha t. Okay. Now, what is T1? T1 is the time when time t is equal to T1, then the thickness delta of t tends to R naught. Right? So this is your thing. So if I substitute these two here, you will get R naught is of the order of square root of alpha T1, or T1 therefore is of the order of R naught squared by alpha. Okay. So now in order to define the early phase and late phase, we can say early phase is when t by T1 is much less than 1, because t is much less than T1 in the early phase, which basically means if I substitute for T1 from its order of magnitude R squared by alpha, that is here, then I'll get alpha t by R naught squared is much less than 1. Okay. Similarly, late phase will be alpha t by R naught squared is much greater than 1. Okay. Now, this alpha t by R naught squared, if you explore that, this is dimensionless because alpha is meter square per second and time is second, so meter square divided by R naught square, which is meter square. So this is a dimensionless number. This dimensionless number is known as the Fourier number, named after the first scientist who actually identified this non-dimensional group. So when the Fourier number is much less than 1, we are in the early phase and we should be using the semi-infinite solid model, and when the Fourier number is much greater than 1, then we will be in the late phase and we can use the lumped capacitance model. In order to use the lumped capacitance model, we will need to have one more condition met, which is also something we will need to understand. We said that C minus T naught, which is the temperature difference between the center of the object and the surface of the object, is much less than T naught minus T infinity. So this is the condition that we wanted it to meet in order to be able to lump the system. So it should also be late phase for this to be facilitated, because in the early phase the Tc is Ti and T naught and T infinity are similar in order. Okay, so your this condition will only be met in the late phase, and in the late phase, for this to be met, what is or in addition required? So that is the thing that we will need to look at. So again, let us go back to this object. So suppose the center temperature is Tc, the surface temperature is T0, and the far field temperature is T infinity. Then if I look at the energy balance at the surface, it will say minus K del T by del N at the surface, okay, is equal to H into T0 minus T infinity, okay, which is the convective rate. So the heat, if it is going out from the body, then minus K del T by del N at the surface will be equal to H into T0 minus T infinity. This is your energy balance. Now let us look at the order of magnitude of T0 minus Tn, del T by del N. Del T by del N, if I take the normal as this direction, then del T by del N would be T0 minus Tc divided by the R0, which is the size of the object. So del T by del N is of the order of T0 minus Tc divided by R0, and so if I use that here, it will become Tc minus T0 divided by R0, okay, and there is a K here, and that is of the order of H into T0 minus T infinity. Okay, so if I group the temperatures to one side, so I'll get Tc minus T0 divided by T0 minus T infinity is equal to H into R0 by K. Okay. Now this is another non-dimensional number, because you look at the left hand side, it's actually a ratio of temperature differences, which is non-dimensional, and on the right hand side, this is H is watts per meter square Kelvin, and this is R0, so it becomes watts per meter Kelvin with multiplication of R0, and this is watts per meter Kelvin, so this is a non-dimensional number, and this non-dimensional number is known as the Biot number, which is another non-dimensional number. And what is it that we are looking at? We are looking at the requirement for Tc minus T0 is much less than T0 minus T infinity. So Tc minus T0 by T0 minus T infinity should be much less than 1. And if I go back here, Tc minus T0 by T0 minus T infinity is actually not equal to, but of the order of HR0 by K. So this Biot number must be much less than 1 in order that this be much less than 1, so that we can apply the lumped capacitance method. So in order to apply the lumped capacitance method, not only we need that the Fourier number be much greater than 1, but we also need that the Biot number is much less than 1. Right? So that is your requirement here. So we have identified two non-dimensional numbers. One is the Fourier number, which is the non-dimensional time, t divided by t1, which is alpha t by r0 square. So it is the time normalized by the characteristic time for the surface phenomenon to penetrate to the entire depth of the body, and this early phase and late phase are when t by t1 is much less than 1 or much greater than 1, and the lumped capacitance method can be used in late phase when the Biot number is much less than 1. Right? So this is all conceptual. Now let us understand how to solve these equations. So let us start with the late phase first, because that is the simplest. So in the late phase, we are saying that the whole body is at any temperature T at any given point in time. We can assume the temperature to be uniform, and the surrounding temperature is T infinity. So we can write the first law for this body. The first law for this body, because it's a closed system, we can actually write it as du by dt is equal to q dot in plus w dot on, and since there is no work being done, this w dot on is 0, so du by dt is q dot in is the first law. And what is u here? It will be the mass of this object, the specific heat of this object, multiplied by the temperature of this object. So it will be d by dt of mCv T of the object is equal to, what is q dot in? If h is the heat transfer coefficient, then the heat flow into the system will be, if temperature is T here, T infinity minus T multiplied by h. So it will be h into T infinity minus T multiplied by the surface area as of the object. So this is the energy balance for this object. So if the object is at temperature T at any given point in time, then the temperature difference between the surroundings and the object multiplied by h into as is the rate at which energy is flowing into the object from the surrounding medium, and that is equal to the rate of change of its internal energy, which is d by dt of mcvt. Now we can take this equation and try to solve this to get temperature as a function of time. So what do you get? You will get dt by dt, taking m and cv as constants and taking them to the other side, is equal to ha by mcv into T infinity minus T. This is your expression. So if I take the minus sign out of this and make this T minus T infinity, since T infinity is a constant, it's not going to vary with time. So then we can actually rewrite this equation in this form. We can rewrite d of T minus T infinity, which is the same as dt, divided by T minus T infinity, which we have actually brought this expression to the left hand side, is equal to minus ha by mcv mcv multiplied by dt. Okay, so if you integrate this expression, you will get T minus T infinity, and applying the boundary condition that at time t equal to 0 the temperature is Ti. So and subtracting those two, we will get this Ti minus T infinity will actually be equal to exponent of minus ha T divided by mcv. I am skipping a few steps and directly writing this. You can verify this by directly integrating this. So you get a log of T minus T infinity here is equal to ha by mcv into T plus C1, and at time t equal to 0, temperature is equal to Ti. So if you substitute that, you get log of Ti minus T infinity is equal to this side is 0, right? So then you subtract these two equations from one another and then take the exponent of both sides, then you get the solution, right? So T minus T infinity by Ti minus T infinity is equal to minus HAT by mcv. Okay, so let's try to analyze this solution. T minus T infinity divided by Ti minus T infinity is equal to exponent of minus HAS divided by mcv to T. Okay, now this particular exponent has multiple interpretations. We can look at them in multiple possible ways. Let's try to look at it one by one now. Okay, the first one is if I write HAS by mcv into T. Now in this, suppose I write mass as density into volume, and I write R naught is volume by surface area. Okay, and then this will become H multiplied by volume by surface area, right, multiplied by density into CV. Okay, and I multiply and divide by, let us say, the thermal conductivity here and multiplied by T. So what do I get here? I get a H divided by R naught and a K here. So I multiply and divide by R naught once again. So I get H into R naught by K. So I have used this, and I have used one of the R naughts, and the other R naught will come below. So it will become R naught square here. So I will get, and this is K by rho C, which is alpha, okay, multiplied by T divided by r naught square. Okay, so this is quite interesting because h r naught by k is your Biot number and alpha t by r naught square is your Fourier number. So your solution therefore is actually a negative of Biot number into Fourier number in the exponent. So this, let me just write that here by erasing this so that I can use the same space. Okay, so if I use that, then this becomes equal to exponent of minus Biot number into Fourier number. So this is one way of looking at the solution. So the t minus t infinity by ti minus t infinity will be equal to minus of Biot number into Fourier number. In this case, remember it's a late phase case. The Biot number is much less than 1 and Fourier number is much greater than 1. So the product will be a finite value typically. Okay, and they can be calculated from the properties of the substance that are known. Okay, so that is one interpretation of this solution. So you have an exponentially decaying temperature difference. So if I plot that temperature difference, T minus T infinity divided by Ti minus T infinity, it will start with 1 at time t equal to 0 and decay like that here. Okay, and what does it decay with? It decays with this as the coefficient. So that coefficient, if you closely look at it, because this product HAS T by MCV is a non-dimensional number, this MCV by HAS is actually going to be another time. Okay, so this becomes then a minus of T by some characteristic time. Okay, so what is that characteristic time or time constant? Because of the time constant, the way in which this approaches 0 will vary. So if something approaches 0 very, very slowly like that here, okay, so that has a very large time constant. If something approaches 0 very quickly like this here, it has a very short time constant, and that time constant will actually be determined by this quantity. So that is the next interpretation that we are going to look at. So let us look at that. So you have HAS divided by MCV. Now we can say that this MCV is nothing but the capacitance of the object, that is the amount of energy stored in the object per unit temperature change, right? So in some sense this is a capacitance term, and 1 over HA is actually the resistance term to convective heat losses or heat gain at the surface of the object. So HAS can be written as another 1 by R. So this actually becomes 1 over RC, which is some form of time constant. So this is actually 1 over some tau for this particular object. So you have T minus Ti divided by T minus T infinity divided by Ti minus T infinity is equal to exponent of minus T by tau, where this tau is nothing but this 1 by RC, which is tau is therefore going to be equal to MCV divided by HAS. Okay, so this is your time constant, and using this time constant you can look at it, and if the time constant is large, then basically this is big or this is small or both. So what does it say? The capacity of the object to absorb energy is very large, the MCV is very large, so a large amount of energy is required to raise the temperature of the object by 1 degree. Or if this is small, then the heat transfer rate from the surface into the object is small per unit temperature difference, because this HAS into temperature difference at the surface is the heat transfer. So if HAS is small, then the heat input or the heat gain by the object is slow. So either if the body has a large capacity or if the inflow of heat is slow, then this time constant is large. Otherwise the time constant is small. So when the time constant is large, then this will decay extremely slowly, and when the time constant is small, then this will decay very quickly. Right? So that is the plot that we showed here. Then when tau is greater than 1 or tau is less than 1. So depending on whether HAS is very large or MCV is very large, the time constants will be large or small. So when HAS is very small, very large, then the time constant is extremely small, so it will be very quick. That is, the heat transfer rate is very large, but the capacity is small, so the object reaches the temperature very quickly. And similarly, if the time constant is very large, that is, the body's mass or CV is very large, and the heat or the heat transfer rate is small, then it will take a very long time to reach the final temperature. So that is the second interpretation of the same problem that you can do. Okay, so both of these interpretations are corresponding to the late phase. We can summarize that. Fourier number is much greater than 1 and Biot number is much less than 1, and in such a case we'll have t minus t infinity divided by ti minus t infinity is exponent of minus Biot into Fourier, okay, which is also equal to exponent of minus t by tau, where tau is mCV divided by HAS. Right? So this is your solution for the late phase or the lumped capacitance problem. So this is your understanding. So in this, basically you treat the entire object to be at the same temperature, because the Biot number is small. The resistance to conduction, that is another thing that I have to tell you. Biot number, what is it? It is H R naught by K. I'll rearrange this to write as R naught by Ka divided by 1 over HA, where A is AS. Okay, you can just multiply and divide by AS here and rearrange that, so you get R naught by KAS by 1 by HAS. So this is nothing but resistance to conduction, and the one below is resistance to convection. So this resistance to convection is happening at the surface, whereas the resistance to conduction is happening inside the body. Okay, and when this is much less than 1, it means that the resistance offered to conduction is much smaller than the resistance to convection. So the body is very good conductor. That is one possibility, that is the K is large, or R naught is small. Either way, this R naught by KAS, the resistance to conduction, is small, and 1 by HA is large, which basically would mean that either H is small or A is small. Whichever way, the heat supply that is happening from the surface is not fast enough to cause temperature gradients inside the object. The object is either small or has a high conductivity, because of which the temperature equalizes faster than the heat supply would change it. So that is why, that is the interpretation of Biot number. It is the ratio of the two resistances, resistance to the conduction inside the object to the convection outside the object. Okay, so that is the interpretation that we will have. So for a small Biot number, you will have the late phase, the lumped capacitance system valid. Okay, so this is one part of our understanding. The next category of problems that we would like to discuss is the early phase. We have mentioned about that. So we had shown the plot of temperature versus time. Okay, and we found that at different points in time, so let us say this is temperature T naught and this is temperature Ti. Initially I told you that the temperature only at the, okay, this is temperature versus x, I'm sorry about that. Initially at only x is equal to 0, the temperature is T0, elsewhere the temperature is Ti. And after a certain time, a certain depth, so let us say this is delta 1 at time T1 is the skin layer thickness, and with progress in time, let us say at time T2 it goes to delta 2, and at time T3 it goes to delta 3, and so on. Now all of these actually can be unified into a single plot of let us say T minus Ti divided by T0 minus Ti. Okay, so this plotted against, instead of x, you normalize it with respect to x divided by delta at any given time t. Then if this is 1, then at all points in time, and this is 1, which is when t is equal to T0, at all points in time you will find all of these curves to just collapse onto just a single curve like this. Okay, so this would be representative of this curve at time T1, this curve at time T2, and this curve at time T3, just by replacing the corresponding value of delta there. This kind of a solution where you can actually collapse similar looking temperature profiles onto a single temperature profile because of the self-similarity, the scaling that expands is used for normalization, is called a similarity solution. And when you do a similarity solution, what happens is two independent variables here, which are t and x, get combined into a single variable called eta, which is x divided by delta of t. Now using this eta, we should be able to collapse the partial differential equation which we started with into an ordinary differential equation in just one independent variable eta. So that is the mathematical method that is typically followed for solving this. We will not get into the mathematical details of solving this, but we will just appreciate that x divided by the delta of t is going to be of the kind x divided by square root of alpha t, because that is what we found delta of t to be proportional to. So you would have this function of t minus ti by t0 minus ti as a function of x by square root of alpha t in the final solution. Okay, so this is what you would expect. We will not go into the mathematical details, but directly we will write the final solution. So the early phase, the solution would look like t minus ti by t0 minus ti is equal to error function of x by twice square root of alpha t. This is the expression that you would get, where this error function is a standard mathematical function coming from the Gaussian normal distribution. So f of x, or let's say f of some value y, is equal to 1 over 2 root pi integral from 0 to y of e to the power of minus m squared dm, if you would like. Okay, so that is the way this is defined. You may remember that this function is the normal distribution function that you normally see. So the solution for the early phase, therefore, is this, and this is a standard mathematical function and its values are tabulated. So we can quickly go to the other slide and take a look at that. So this is what it looks like. So this Gaussian error function is actually plotted or printed or tabulated as a function of the x. So if x is on this column, error function of x is in this column. So all you need to do, and the error function is defined in this fashion as I just told you. And there is also something called a complementary error function, which is 1 minus error function, which is basically directly related to this. So if I go back to this screen, the error function of x by square root of alpha 2 alpha t. So if I know the time, and if I would like to find out the temperature at location x, I use this x and t to evaluate this x by 2 root alpha t, and go to the error function table and find its error function, and that will give me t minus ti by t naught minus ti. Since ti and t naught are known, I can calculate the value of t. Okay, so once I specify the x and t, I should be able to get the value of the temperature t. So that is the formula that I'll use, and the table that I need to use is this table of error functions. Okay, so that is the solution for the early phase problem. So let us go back and quickly summarize. So the late phase solution is the solution for lumped capacitance, which is shown on this table, where if I know the time, because the temperature is not a function of x anymore, it's only a function of time. It's the whole body is taken as a single temperature. Once I specify the time, and I know the values of mCv, because if it's a body of mass m whose specific heat is Cv, and its surface area is As, and the heat transfer coefficient of the medium in which it is dropped is known as h, then I can calculate the tau, and substituting in this expression, I can get exponent of minus t by tau, which will give me the value of t minus t infinity by ti minus t infinity. And once I know the value of t infinity and ti, I should be able to get the value of t. So this is your late phase solution. It can also be done by calculating Biot and Fourier numbers, using the definition of Biot number and Fourier number as we had seen earlier, and using this expression. Right? So that is the late phase. And the early phase uses this error function method to solve. Okay, so you, given the values of x and t, you calculate x by 2 root alpha t, and find out its error function using the error function table, and from that you can calculate the temperature. Right? So that is the early phase. Now the question arises, what will we do if the problem is neither of early phase nor of late phase? Then we will need to solve the differential equation completely. Okay, so the differential equation is 1 by alpha del by del t of temperature is equal to del squared t by del x squared. So this is normally solved using the method of separation of variables. I will not go into too much detail of that, but all what you do is to write temperature is a product of x, which is a function only of x, and tau, which is a function only of t, and substitute that into this and resolve it into two separate equations, one in time and one in temperature, and then get the solutions for one in x and one in t, and get the solutions x and t using ordinary differential equation solution methods, and put them together here. Okay, so in the present case, we normalize this equation to write it in terms of theta, which is t minus t naught divided by ti minus t naught, okay, or rather t minus t infinity divided by ti minus t infinity, if you would like. Okay, now this is the function which we will write in place of this t. Anyway, t naught, ti and t infinity are constants, so this equation can directly easily be translated to write in terms of theta, and theta you write it as a product of these two functions. So you write it like this is t minus t infinity divided by tc minus t infinity, where tc is the center line temperature of the body. I'll come to it with the geometry. This multiplied by just Tc minus T infinity divided by Ti minus T infinity, where let us say the geometry that I am trying to solve for is a one-dimensional slab with this as the center line, and so this is, say, x is equal to 0, this is x is equal to L, and x is equal to minus L on this side. Now you are solving for one half of the domain, x is equal to 0 to L, using this equation. So the boundary conditions will be at the center line, because of symmetry, x is equal to 0, del theta by del x will be 0, and at x is equal to L, you will have the convective boundary condition in the case where there is a h and t infinity, and a fixed boundary condition. So we'll write the convective boundary condition. So that will be del t by del x with minus k, which is the energy arriving at the boundary x is equal to L by conduction from inside the domain, would be equal to h into t at L minus t infinity is the boundary condition. So with these two boundary conditions, we will solve this equation, and then the temperature at x is equal to 0 is theta c, okay, which is basically given as Tc minus T infinity divided by Ti minus T infinity, which is this. So this centerline temperature is only a function of time. Okay, with time the centerline temperature varies because this is already x is fixed as x is equal to 0. So this is only a function of time, and this then, once I know the centerline temperature, this is a function of x and t, and relative to this, this will become a final function only of x. So you have this x of x given by this expression and tau of t given by this expression. We will not go into too much detail of this, but what we will understand is that by separation of variables, we will separate it into two functions, one this and one this, and get the solutions for both of these and plot them in the form of charts. Okay, so the charts on which these are plotted are known as the Heisler charts. Okay, so you will have two Heisler charts, one for Tc minus T infinity divided by Ti minus T infinity, which is a function only of t. Okay, so non-dimensional value of temporary time would come in the form of the Fourier number, and the parameter for this, which signifies the properties of the material and the medium, is the Biot number. So in function, as a function of Biot number and Fourier number, this value would be obtained, Tc minus T infinity by Ti minus T infinity will be obtained from one of the charts. So this will be the first chart, and the second chart, once I have the Tc value from this chart, I will use that in this, saying that this is T minus T infinity divided by Tc minus T infinity, okay, where this Tc is already known to me. This is going to be equal to some function only of x with again the Biot number as the parameter. Okay, so these two charts then put together, I get this from the first chart and this from the second chart, and multiply these two to get T minus T infinity. So the Tc minus T infinity should get cancelled, T minus T infinity by Ti minus T infinity. So the product of, let us say this is theta 1 and this is theta 2. So theta will be equal to theta 1 into theta 2. So you get the value of theta 1 from one chart and theta 2 from the other chart, and multiply, and you get the value of theta, which is T minus T infinity by Ti minus T infinity, from which you can calculate the value of Ti. So now let me go back to the other presentation that I have, in which I'll be able to show you the charts. So let's move on to this presentation. Now here, this is the Heisler chart for the plane wall. Notice that there is a kink that is seen here because the scale of the x-axis is different in the different regions. Okay, otherwise it's the same function. Here it is enlarged so that these values are all not cluttered and complicated here. So this corner is also enlarged so that you can see those lines very clearly, otherwise all of these lines will be merging there. So instead of showing it on a rectangle of this size, it's enlarged into a rectangle of this size so that you can see the lines very clearly. So what is this showing? On the y-axis, it is t naught minus t infinity by ti minus t infinity. T naught is the same as tc that I was showing to you. So this is tc minus t infinity by ti minus t infinity on the y-axis. And on the x-axis, you have the Fourier number, alpha t by L squared. In this case, the characteristic length is L, which is the half length of the slab that we showed on this slide. Right? So the half length of the slab, or the half width of the slab, x is equal to 0 to L. This L is the characteristic length. So your Fourier number is calculated using alpha t by L squared. So that is what you get on the y-axis here, or on the x-axis here. So this is your Fourier number, and the y-axis is the theta, and the lines are for different values of 1 by Biot number. Okay, so for the simple case where the wall temperature is specified, we can take the wall temperature is equal to the surrounding temperature. T naught and T infinity are equal because of infinite value of H, which is infinite value of Biot number. Infinite value of Biot number. So 1 by Biot number will be 0. So you'll need to look up this 1 by Biot number equal to 0 line corresponding to the specified wall temperature line. Otherwise, for a given value of H and K, you can calculate the Biot number. The Biot number is defined as HL by K, where L is again the half width of the slab. Using that, you can calculate the Biot number and Fourier number, and from this chart, using the Biot number and Fourier number, you can look up the value of theta c, okay, or Tc. Once the Tc is known, you go to the next slide, which is the T minus T infinity by Tc minus T infinity as a function of Biot number, 1 by Biot number, which is K by HL on the x-axis for different values of x. So this is plotted for x by L equal to 0.2, x by L equal to 0.4, x by L equal to 0.6, x by L equal to 0.8, 0.9, and 1. So depending on the location at which you would like to find the temperature, you calculate the value of x by L there. If it is not equal to any of these, you may need to interpolate between them. Otherwise, for the given value of inverse of Biot number, at that location, the theta value can be read. Okay, so this tells you what is the value of theta 2, and this tells you what is the value of theta 1. So the product of theta 1 and theta 2 will basically give me theta, which is the function that I need, which is t minus t infinity divided by ti minus t infinity, from which I can calculate the temperature. The same kind of solutions are also available for cylinders and spheres. So I'll show them quickly. So the cylinder also has this, except that the definition of Fourier number is in terms of R0, which is the radius of the cylinder, and Biot number is in terms of HR0 by K, where R0 is the radius of the cylinder. Okay, so that is about the cylinder. This is for theta 1 of the cylinder, and this is for theta 2, where instead of x by L, you have R by R0. So at any radial location, you can find out this. In the same way, you have functions for sphere, which is again R0 is the function here. So Fourier number is in terms of alpha t by R0 square, and Biot number is in terms of HR0 by K, and this is the chart for theta 1, and this is the chart for theta 2, and you get the product of those to get theta. The last but not least, I would like to show you another chart, which is called the Grober chart, from which the heat transfer across the wall can be calculated. This Q naught is the maximum possible heat transfer from a given body. So suppose a body is initially at Ti, and the surrounding is at T infinity. Let us say Ti is greater than T infinity, as we had initially done. So the maximum amount of heat that can be transferred is when the whole body goes to the surrounding temperature, T infinity. So this Q naught would actually be equal to mass of the body multiplied by specific heat into Ti minus T infinity. So that is Q naught. And Q is the amount of heat transfer that has happened until a certain time t. Okay. So the Q by Q naught can be evaluated again as a function of Biot number and Fourier number. So you compute the Biot number and Fourier number for the time at which you would like to find out how much heat has transferred, and At that, you calculate the BI squared FO and the BI. So for a given value of BI squared FO and for a given value of BI, okay, so what is the value of Q by Q naught is something that you can read. Say for example, if the Biot number is 1, let us say 1, okay, and the BI squared FO, BI is 1, and let us say Fourier number is also 1. So then BI squared FO will be 1, so we will be on this line. So the point will be this, so the value of Q by Q naught is 0.5, which basically means the total amount of energy transferred until the time corresponding to Fourier number equal to 1 for this body will be half of the total heat transfer. So that is a way in which you can actually calculate what is the change in internal energy as a function of this one. This is for the plane wall. Similar Grover charts are also available for the cylinder and the sphere. So that brings us to the close of transient heat conduction. So what all did we study today? So we studied the two extremes of the transient heat conduction model. One is the early phase and the other is the late phase. We found that the early phase can be treated using a semi-infinite solid model, and the solution comes in the form of an error function because of the similarity. And the late phase can be treated as a lumped capacitance problem if the Biot number is sufficiently small, and the solution comes as an e to the power of minus t kind of form. And there is a time constant which is a function of the HA and the MC of the given body. And when neither of these approximations can be used, then you need to solve the full equation. The full equation has been solved and plotted in the form of charts from which we can look up the values and calculate the values of the temperature. So that brings us to the close of transient conduction. It's quite an interesting and intuitive topic, and I have uploaded the source from which I have taught this, because this approach I have always liked it to be more elegant because it's easier to get the physical understanding of the problem from the mathematics of it without going too much into the mathematics. So I would like you to go through the handout from Bejan that I have uploaded for transient conduction, which gives much of this information. And the bonus is that the end of the problem and the end of the chapter also has some interesting problems, and I always liked Bejan's problems because they were quite insightful, right? So kindly take a look at that. So we have now completed steady state and transient conduction in these 3 lectures. They have been reasonably loaded. We will have a tutorial sheet on this in the coming week. In the meantime, you solve the tutorial sheet number 4, and in the coming week I will upload the solution of the tutorial sheet number 4 and also give you tute sheet number 5 on which we can start. The classes in the next week will start with radiation heat transfer, because radiation heat transfer can also be covered in a span of about 3 to 4 lectures. And once that is done, in the remaining number of lectures that we have available, we had about 16 left. So out of which 3 have been taken for conduction and maybe 4 for radiation. We'll have about 8 or 9 lectures on which we can do the convective heat transfer module. Okay. So at this point in time, I'll take your leave. Take good care and stay safe at home. But at the same time, don't take it to be holidays. You have had enough holidays. So now let's get back right on to work. Thank you and bye-bye.